My name is Kasia, and I'm going to talk to you about interpretable machine learning. And I will use a specific use case of LIME framework. Just out of curiosity, how many of you deal with machine learning or build machine learning models on a daily basis? Okay, quite a few of you. And how many of you have heard about LIME? Okay, not bad, not bad. So it's great because if you didn't hear about it, you'll learn about it today. But before I start, I would like to say something about myself. So I come from Poland, and my background actually is in biology. So I did my master's degree in biology in Krakow, after which I moved to Sweden, to a small academic town, Uppsala, where I did a PhD in evolutionary biology. And my degree took me to different weird and wonderful places. I spent a lot of time in the forest on a Swedish island, Öland. Did a lot of lab work in Lund, Swedish academic town. I did a lot of analytics work as well. But even, I should have known that means something, I spent a year at Imperial College working on malaria transmission. So eventually I moved to London in 2014, and that became my home. And ever since I've been working on, in analytics and data science roles. And currently I'm a data scientist at Aviva. So going back to, there's one more thing I want to tell you about myself. So data's a big part of my life. But unlike some of the presenters that were here before, it's not the only part of my life. So when it comes to data, obviously I try to teach myself new methods and data science applications through online courses, meetups. I'm quite a engaged Twitter user, especially in our community. I'm a co-organizer of Our Lady, so that other meetup, but I also run a blog on data science using R. But as I said, I try to do it when I have time, but these two little creatures don't leave me with a lot of it. So this is really how I spend my time, and it's usually away from computer screens. So if I don't spend time with them, I try to hike, do jigsaw, bake. So I think in that sense I'm not this ultimate geeky data scientist. Anyway, now definitely going back to interpretable machine learning. So whenever we talk about interpretable machine learning, we really talk about the black box algorithms. And what I mean by that, so for me, a black box is really a system that performs a certain behavior to the input data that we feed into it, and gives us an output, but we don't really understand how we get that output. So, and I think especially recently, it's a huge hype around black box algorithms because these are the algorithms that tend to be most accurate, speaking, let's say neural nets, right? So, but how did we get there, and is it really that black boxy? So let's say we try to answer a question, will the loan default, right? We receive an application and we try to judge that. And obviously this could be any classification question, whether it's that cell is a cancerous cell, or whether the prisoner we give parole to will commit a crime, or whether whatever machine will break down, right? So it's just a matter of a classification problem we deal with. So let's say we stick to the question about the loan, and we have a certain information about the applicant, and obviously this information alone is quite useless. So to really make use out of it, we need some historical data. We need to really understand how different applicants with different features ended up in the past. And let's say if we have very few variables and not lots and lots of data, we can actually draw certain conclusions that are very easy to interpret. So here obviously we can run just a linear model, draw a line between the two classes, and and see that by following certain rules about the predictors, we get certain outcomes. So it's fully interpretable. What about non-linear relationships? So it still is not so bad, because let's say we can use a decision tree, and again, we can follow rules containing that tree and still kind of select groups of classes and see where they came from and why they were classified this way. So again, it's still interpretable. The problem starts with big data. So big data creates more dimensions, obviously more relationships between predictors and outcome variable, but also more complex, if you will, landscape of those relationships. So how do you really create a model that gives you information about all those intricate relationships? So again, in data science, we're not completely helpless. Let's say we can use feature importance plots. So this will really inform us how important the feature was in predicting the outcome. So let's say when we have random forest, we can, let's say, judge that the more important the feature, the higher up on average we found it in making those decisions about outcomes, let's say. So it is something, it's not ideal, because, for instance, it doesn't give us any indication of direction of the relationship, whether that direction is linear or not. So it still leaves us with a lot of work to do in order to actually understand how the features and outcome relate to each other. It gets better if we can use partial dependency plots. So those plots basically show us the relationship of marginal effect of each of the predictors has on the response variable. So you can see we can pick a number of, let's say we can run the feature importance plots. Then we can pick the top important variables. We can see how they relate to outcome variable. And then even if this relationship is non-linear, so for instance, there's no real relationship that gets negative then positive, we can still see that and interpret that. So it's great. However, we are not able to produce those dependency plots for every classifier we have. So for instance, we can't do that for neural networks. And then finally, well, I'll give you examples. There are more tools that we have. But for instance, you could go Bayesian, and you can create Bayesian network, which is, I would say, a bit of an outlier in machine learning models, because it goes away from this assumption that we have a response variable and predictors, and it basically shows you dependencies between all the variables you take into account, including the outcome variable, and it can present you with weights. So it gives you an idea how variables depend on each other and how strong that relationship is. However, Bayesian networks tend to be not as accurate when it comes to predictions as, let's say, neural nets. And altogether, all those tools have definitely one downside. So they won't be able to tell you why this particular observation was classified one way or another. So it can give you an idea of the global behavior of the model, but it won't really tell you why this particular observation was classified this way. So you can imagine, even if you have, let's say, this is the landscape, and here you have a lump of observations that tend to be classified in a certain way, you won't be able to see that in those plots. So what can you do? So before you think what you can do, you can think about accuracy and interpretability trade-off. So I think it's a common agreement in machine learning field that such a trade-off exists. And some people would draw a line reflecting that relationship this way. So those models that are highly interpretable are usually less accurate than those that we don't really understand. So the question is, what about models that we could cluster here? So highly interpretable and highly accurate at the same time. So So this is where LIME comes into play. And LIME is really the abbreviation for local, interpretable, model-agnostic explanations. So by interpretable explanations, I really mean that we're able to understand what model does, which features it picks on, in order to create or develop predictions. By model-agnostic, I mean that this can be applied to any black box model that we know today, and also the model that may be developed in the future. So, and in essence, the assumption is that any model, for instance, if you try to apply LIME to linear regression, that is highly interpretable linear model, obviously, it will still assume that this is a black box. So assumption is every algorithm is a black box algorithm. And finally, local one means that is observation specific. So it gives you this information about every single observation you have in a data set. So this is new work. So the work on LIME was published only last year by the research team at the time based at the Washington University. And even though it's quite a recent invention, if you will, the great thing is that it's available in both Python and R. So again, maybe let's talk a little bit about what I mean by local. So when we said this was the landscape of relationships between predictors and outcome variable, and we don't really get much from having a global view of that, or at least in many businesses and industries, you don't. So LIME, what does? It ignores that, and it goes on a very local level. It picks the observation, or sometimes a cluster of observations that are very similar, and gets to the point where you become so local that you actually can use a linear model to understand the relationship. So, and it will be highly accurate on that local level. So, forgive me if you're not interested in that technical details, but I noticed in many talks on LIME, those technical details, how actually LIME works are skipped, and I think it's important to really understand why it's so powerful. So essentially what LIME does, it takes an observation and creates essentially fake data for it. It takes all the data you have for that point, all your predictors, and it permutes it in different ways. So it creates fake data sets for each observation. And then it calculates distance metric or similarity score between those fake data and the original data. So we know that the data we created, how similar they are to the original ones. Then it takes your black box algorithm, let's say neural nets, and it makes predictions on that new data set. Finally, it tries different combinations of predictors, let's say m numbers, so usually it's a small number of predictors, to figure out the minimum number of predictors you have that gives you the maximum likelihood of the class that was predicted by the black box. So this is important because this is, let's say, if you have 300 features that went into your model, you end up with a handful that is most informative to drive that prediction. And finally, it picks those m features, and together with those similarity scores, it fits them to the simple model, let's say linear model, to derive weights or coefficients. And those coefficients will serve as an explanation for that particular observation on a local scale. So hopefully that makes sense. Also, what is very good about LIME is wherever I put a star, these are the points at which you can make decisions, or you can optimize your explanation. So you can decide how you permute your data. You can decide what is your similarity measure. You can decide how many features you end up with, or you can choose the simple model that will be fit to those data. So it's quite flexible. Okay, so this is Lyme. And someone would say, okay, do I really need it if I have a model that performs really well? If I have a model that has a very high accuracy, do I really need Lyme, or can I trust this model based on accuracy alone? Well, you can't. So the reason for that is that without knowing what model picks up on, you don't know if it's the genuine signal, you don't know if it's noise, some correlations, something completely irrelevant. Just to give you an example, let's say we have a model that distinguishes between huskies and wolves. Quite challenging task, but let's say this is model performance. So it performed very well because it was correct in 5 out of 6 cases. And there's only one case here that went wrong, right? So it performs well. I would be quite happy with it. But then when you actually see the explanation for this model, you realize that it's rubbish. Because here is the picture on the left-hand side, the original picture, and then on the right-hand side you see which parts of the picture were informative to the model for making predictions. So you can see for predicting huskies, it's usually elements of a husky here, elements of a snout, of a face. So that's a sensible behavior. But for wolves, all it picks up on is snow. So we just built a great snow detector. And so what that is very accurate, it's a bad model. You can't trust it. And you wouldn't know that without having this explanation in the first place. Another great thing about Lyme is that you can apply it to also NLP models, so in text analytics. So let's say you try to distinguish between articles or blog posts that were written either by atheists or Catholics. And then you run a model that performs, I think in this original example, it was 94% accurate. Amazing, right? But then you check which are the hints that model picks up on. And okay, I can see that maybe if your email address contains edu, then probably, you know, in the case that you're educated, perhaps that means you're less likely to be Catholic. But then there are things that don't make sense at all. So obviously, model is not sensible here. It picks up on things that don't make sense for us. So we can't trust it. I used Lyme in a very simple example for understanding a model that classified or distinguished between cancer and benign cells, or malignant and benign cancer cells. So hopefully I can show you my code very quickly. I publish on my blog, so no live coding, nothing. But just to give you an idea how we can perform in a simple classification problem. So for this example, I used pretty famous Wisconsin breast cancer dataset. It's a perfect dataset for dummy presentations. It's quite small. It's just only about 700 observations. It's quite well known and understood. So after doing some very simple data cleaning, getting names right, removing sample IDs, removing order from factor levels, I start H2O local instance, and I set up my data science pipeline. So basically, I split my data set into training, validation, and testing sets. And then I run excellent H2O AutoML function. So basically, this is the function that optimizes and chooses classifier for me. And only after 60 seconds, I already get excellent results. And no surprise here, these are the top performers, top 6 performance, top 2 neural nets, the 4 gradient boosted models. Again, no surprise. And then I simply divide this test set into observations that were correctly classified or incorrectly classified. So the rest is not really important. I mean, I'm doing some performance analysis. This is not really important. But what you probably want to see is this, that I ran Lyme on correctly predicted observations. And you can see for benign cases, is something that makes sense to us and would make sense to a medical doctor. So let's say the cell size was small, the shape was regular, the bare nuclei, I believe it wasn't visible. I'm not sure here what that means, but some of those features are quite intuitive, and also number of mitosis was somewhere an example was low. So it all makes sense. I would say that, okay, if I see a model performing this behavior, I would say it's sensible. Similarly, with malignant cases, you can see the number of mitosis is high, cell shape is irregular, cell size is big, and something called clump thickness is high. So again, it makes perfect sense. If I show this model to a doctor and say, okay, are you going to use it in your practice? Probably the doctor would trust this model. However, when we go to incorrectly predicted observations, you can see again, like here, this one was predicted to be benign, and its size was small. The size was small, the shape was regular, but there were other things. Let's say like bare nuclei value was high. So what it really tells me is that there were certain behaviors, so certain features for that observations that are typical for normal cell. And that's why model misclassified it. So even though the model was wrong, I still have trust in it because its behavior was sensible. So this is that example. And now, why this is important? So it's important for, I would say, two areas of reasons. And one is more technical. So obviously, it's for developing trust we have in our model, in being able to predict how model will behave on unseen data, and also how we can improve our model based on explanations. And in all those three areas, Lime was proven in research to do really well. So for instance, when it comes to trust, when the researchers showed that people who are not familiar to Lime and not familiar to machine learning at all are being able to interpret the explanations very easily, and also based on those explanations are able to tell good models from bad models. Also, people who have access to explanations are able to predict how model will behave on unseen data better than people that don't have access to those explanations. And finally, when it comes to improving the model, and this is absolutely awesome. So if you take non-machine learning experts who have access to explanations and you ask them to do feature engineering, to chuck features that they think are not important and maybe engineer features that may be important, they're able to improve the model much better than machine learning experts that don't have access to those explanations. So from a technical point of view, having access to those explanations is absolutely critical. But there are much more important reasons than just technical ones why we need those explanations. On a legal side, obviously starting from May 2018, we'll be obliged to comply with GDPR, which basically means, or one aspect of GDPR is that the customers have right to an explanation. So for companies that incorporate automated decision-making process, they will have to provide explanation why a particular customer was refused a loan, was not recruited, and so on. On a slightly different level, something that Cathy O'Neill calls weapons of math destruction, so which are models or algorithms that have three properties that are obscure, we don't really understand them, that work at scale, are ubiquitous, and also that damage. So whether this is assessing someone's performance, whether it's granting parole to a prisoner and predicting whether they will commit a crime, this is really important. And if we can't understand those models, can't access those models, we are at risk of harming vulnerable people. But still you can think, okay, those hidden models, blah, blah, they are not really everywhere. They affect only certain demographics. But no, think about something that Tufekci talked about in TED Talk. in old days, when it comes to marketing, if we wanted to sell someone a trip to Las Vegas, we would target demographics that we know about. We would target, let's say, men between 20 and 30 years old, older people with certain financial profile. And we would know exactly who we're targeting and why. Imagine these days if we wanted to develop an algorithm that simply sells trips to Vegas to whoever is going to buy them. And then, without knowing about it, it turns out that the algorithm targets, let's say, people with bipolar disorder who are about to enter a manic phase. And therefore, they are more likely to overspend, to engage in the gambling and so on. We wouldn't even know about it. And this is about marketing. This is about personalization. This is about something that will or is affecting us right now. So I don't want to leave you with being depressed about it. But what I'm trying to leave you with is the message that this is everyone's responsibility. It's not only policymakers' responsibility to make sure that we understand our models. This is the responsibility of analysts, of data scientists, machine learning researchers. And we live in amazing times to be able to create those models, but at the same time they come with risk of harming very vulnerable people. So this should be the priority number one for us, to develop those tools and frameworks for understanding our models. And LIME framework is a great place to start. Thank you very much. I'm not sure you understand the data cube concept, but essentially LIME should be incorporated at the point of developing your algorithm. And before it's productionized, before it's deployed, it has to be acknowledged and confirmed that it doesn't it does comply with GDPR, essentially, that it doesn't rely on any biases that we have, that it's not being racist, it's not being sexist, right? So that predictions are not being made based on your gender or your race. So that's what LIME could be based on. So that's what LIME could help you with.
The data you have originally, how do you address it? So yes, you run your model, you test it with LIME, you see that it doesn't make sense. The underlying logic for the model, even though it performs well, would not generalize well, or is flawed. How do we address it?
No, but that's exactly the point. So for instance, with, let's say, atheists and Christians example, if you see that your model picks up on the data that is not actually part of your text, you can easily modify your data so that it contains only text. With image, I'm not a deep learning expert. I'm not sure what you can do. Perhaps you could trim pictures so that they ignore the background, right? But it's definitely the first step for understanding what goes wrong or right with the model, and then it opens the ways for you to decide how you can modify your data set or features that are incorporated to make it more trustworthy, really. I don't know if you...
Thank you for the talk, it was really interesting. Can LIME take apart ensemble models and explain them in a really nice way? And is it exactly the same technique, no matter how many?
Literally today we had discussion about this. So, in example, oh no, it wasn't that. Let's say if you build an ensemble model that relies on one data set, I can see how LIME can be as easily applied to that as to any other classifier or any other learner, right? But I'm not sure how LIME would behave to what we know today if we build an ensemble model that relies on different models that were fed different data sets. So for instance, I have a model for churn, I have a model for something else, and I use different data sets for those, and then I try to create an ensemble model based on these two. I'm not sure how it would behave, to be honest. But again, Lime is out in, it's open source. Python packages are out there. So it's really a matter of research. How are we going to modify that? Yeah. Again. Okay. I don't know where's it going. I think so.
Yeah, I've got it's a very short question, but to reduce the number of features, do you use PCA for that?
So you mean this, any particular example, or?
Just in general, do you use that to reduce the number of features to like a fraction? You're talking about rating them using a tree.
Sometimes, I mean, if I deal with like hundreds and hundreds of features, I would use PCA for that. But if I have anything up to 100 features, and again, depending on the model, but for instance, with something like random forest, I would literally use feature importance. I forgot the name for this. There is a very useful function in the random forest package now that essentially shows you the performance of the model given the number of top important features. So whether you focus on 5, 10, 50, whatever. So then I would really use that to guide my decision where is the cutoff. So basically the maximum number of features I can get rid of without losing performance.
It looks like Lime uses these squares to pick which features could you very briefly go through the process of starting with a data set and preparing it in order to do Lime, as opposed to just going to try to make a predictive model? What extra steps are necessary?
The steps are really not that many. So essentially, you follow your pipeline or your framework as you would have. So for instance here, this is essentially the whole bit here. Is essentially, there's nothing new about creating the model. So I have my data, I split it into train, validation, and train sets. I run the model. Obviously here I used H2O AutoML thing, but this is the model I have. I use it to predict my test set, and that's it. And still I have all the performance analysis where I have my accuracy, I have my misclassification rate, recall, and so on. So at this point, most people would stop, right? They have the performance metrics, they're either happy with them or they're not. But what do you do? I mean, it's a bit different now because there's some fiddling going on to transform H2O model so that it fits into Lime. But if you didn't use H2O, let's say, you could literally just add it here. So here you create the explainer, you define your train set, you define your model, so this is the leader, and that's it. And then you apply this explainer to, well, here I split the data set, so I applied it to different data sets, but you would just apply it to your test set.
So in order, you just have to split the data set and make 2 additional function calls to use Lime, and I imagine in Python it's very similar.
Must be similar. So here, as I said, I did that for kind of demonstration purposes to show, okay, how do we understand the model with correct predictions and incorrect predictions. But overall, you can just apply that explainer to your test set, and that's it. So that's one additional function call.
I would like to build on the question when I curious about feature importance. So, because it is local, you can have a very complex model with many features. You look at one particular point in the data set, you generate new samples, you see, and the predictors that make sense for this point, and the most important ones are at the output of Lime, make sense. But it doesn't mean that those are the same predictors which should be the most important elsewhere.
Exactly.
So you tested for all the boarding points between classes and it's
Yeah.
How do you approach this one?
You see, that's what annoyed me about Lime when I first started using it, because I thought, oh, I'm used to those feature importance plots, and they're like fixed, this feature is important always, and I know what to expect. But then it made me realize the more and more I worked with it and I tried to understand it, it's really this. That you don't have one pattern of those relationships between predictors and outcomes. And in that sense, you can go here and understand why your point is classified this way here, and it may differ from why it's classified like this here. So this is what really Lime gives you.
If we want to make sure that the model on the whole feature space and for all the observations is justified, logical perspective, mathematical perspective, and so on, so we would need to apply this Lime analysis to all the points we have. We can't rely on just point.
I will try to show you one slide, and this comes from the presentation that was originally made by one of the creators of Lime, and I haven't used that functionality personally, but I know that in theory it's possible. So let me just very quickly, I don't know how much time we have, sorry Joe, we're running late. So, just to give you an idea, as I said, I haven't used it myself. That is this. That essentially, apparently, I don't know if that happens at random, or the Lime has an algorithm that picks those kind of edgy points that would guide your view of what global model looks like. So as I said, I personally didn't use it, but this comes from people who actually invented Lime. So in theory, it should be possible to focus on most informative points and see how that relationship changes. Yeah.
The next step.